Okay, so welcome back, everybody. So last lecture we ended with an example, or a couple of examples of using this theorem that was very handy for computing some residues. And so the idea of the theorem was that if we were dealing with a function that had a pole of order m at a point, then what this meant is that we could rewrite that function the following way, so that this function could be rewritten as f of z is phi of z over z minus z naught to the m, where this phi of z is analytic and non-zero at the z naught. Okay, so in that case, if this is a pole of order 1, so if this is a simple pole, then we could actually compute that residue just by evaluating this thing evaluating the numerator here in this form, phi of z at z naught. If not, then we could still compute the residue pretty quickly from from this fact by computing the m minus first derivative of phi and evaluating that as z naught and dividing by this constant m minus 1 factorial. So this was a handy way. We did a couple of examples of this. So here's another example of this where we can use this also when we're talking about multi-valued functions. So for instance, another example of this, so let's say that we have the function that is log z cubed over z squared plus 1. Okay, where when we write this, the branch that we use for log z, so log z we know is ln r plus I theta, and the branch in question we'll say is the one with the branch cut on the positive x-axis, so theta is between 0 and 2 pi. Okay, so this is the branch to be used. Okay, and so let's compute the residue of f at z equals I. Okay, so how do I compute this? So if this is the thing that I want to compute, I want to rewrite this thing here. Well, the denominator of this f, of course, factors. Right? So this is log z cubed over this factors as z minus I, z plus I. Okay. And so if I want to write this as phi over z minus I here, in such a way that phi is analytic and non-zero at I, well, clearly I would do that by taking this part right, as my phi. So I can write this as phi of z over z minus I, where phi of z is equal to log z cubed over z plus I. Okay, so one thing we note is this is analytic at I, so this is analytic, so phi is analytic at I. In fact, I mean, this thing is this thing's not just analytic. This is entire. This is analytic. It's analytic everywhere. So this is I don't even need to include the at I here. This is just sorry, it's not entire. It has singularity at minus I, but it's analytic at it's equals I. So we don't care about anything else. It's analytic as equals I, and we have to check that this thing is non-zero at I. So phi of I is using this branch. This would be ln of 1 here, because r is modulus of I. So this is this is ln of 1 plus my argument here for I is pi over 2. So this is I times pi over 2. And I'm cubing that all over I plus I. Right. So this is, so that's 0. This would be I cubed times pi over 2 cubed over 2I. So this would be minus pi cubed over 16. Okay. Which is non-zero, right? And the reason, of course, I have to check that is this part of my theorem, right? So my requirements in order to be able to write what's in the boxed thing here is that I can put it in this form where phi is analytic and non-zero at that point. Okay, so this tells me immediately then, because the exponent on z minus I here in the denominator is 1, that this is a simple pole. Z equals I is a simple pole. It's a pole of order 1. So this implies that z equals I is a pole of order m is equal to 1. Which means that my residue at I of f is, according to that theorem, phi of I, which I've already computed, to be minus pi cubed over 16. Okay. And there we go. Okay. So there's another example of how this works. Okay. Now let me do one more example that illustrates that while this theorem is really nice, it's not something that I'm going to always be using, even when I have f that in a form that seems like it might be really nice. So a lot of times it is still better to actually use just the Lorentz series expansion. So many times the Lorentz series is still the most direct way. Of computing a residue. So to see an example here, if the function in question is hyperbolic sine of z over z to the fourth, we actually did this yesterday. All right, so this has a pole of order 3 at z equals 0. So this has a pole of order 3 at z equals 0. And we found that by actually just writing out this Lorentz series. Let me see if I can find the sheet where we did that. Yeah, here we go. So for sinh z over z to the fourth, we found, oh, well, this is 1 over z to the fourth times my Maclaurin series expansion for sinh z. So this was the Lorentz series I had. Here's my principal part of the Lorentz series. The residue was 1/6, right? Notice that is a lot more straightforward than trying to use this theorem, because note, I can't say that phi of z is sinh z and write f of z is phi of z over z to the fourth. Why can't I do that? Because sinh 0 is 0, right? Since phi of 0, which is sinh 0, is 0. Okay, and this thing has to be non-zero at the point you're computing the residue at. Okay, so that's no good. All right. So using the Lorentz series is better in this case. So using the Lorentz series directly is better in this case. Okay, and so we had previously found that the residue at 0 of this function is actually 1/6. Okay, so that is the better way of doing it in this case. Okay. All right. And of course, sometimes it is actually better to do a combination. So sometimes you can do a combination approach where you combine the Lorentz series approach with this theorem. Okay, and so there's a quick example of that I won't work through. So here's a quick example that you can work through on your own. So this is the function that is 1 over z times e to the z minus 1. Okay. So the idea here is, well, maybe we can go ahead and do this. Yeah, let's do it on the next page. So we can sometimes combine the approaches. So we can combine the series method with this theorem. So here's a good example of that. So if f of z is 1 over z times e to the z minus 1, then to see how to combine series with this theorem, recall Maclaurin series for e to the z. This is the one you should always have remembered, right? Okay, so there's my Maclaurin series for e to the z. This is valid anywhere. Okay, so then z times e to the z minus 1. What does that look like? This is z times, since it's e to the z minus 1, this constant term is gone, so this is z times z over 1 factorial plus z squared over 2 factorial, and so on. Okay. Alright, so now everything here has a constant term, or sorry, everything here has a z common to it. So I can factor that out, and this is z squared times 1 plus z over 2 factorial plus z squared over 3 factorial, and so on. And that's valid everywhere too. And so, since f of z is 1 over this thing, I can actually rewrite this as phi of z over z squared, right, where phi of z is the reciprocal of this function here, 1 over 1 plus z over 2 factorial plus z squared over 3 factorial, and so on. Okay. But what's cool about this is phi is analytic at z equals 0. And phi of 0 is, when I plug in 0 here, I get 1 over 1. This is just 1, which is non-zero. So, what does that mean? That means that this function actually has a pole of order 2. Right? i.e., f has a pole of order m equals 2 at z equals 0. So this is something that doesn't look, this is not apparent just from looking at this thing, right? you maybe wouldn't have guessed that this is the case, or maybe you would have. You'd said, okay, well, one of the, one power in the order comes from this term, and the other one comes from this term, because when z is equal to 0, this is 1 minus 1. So the 0 here gives you 1, and this thing gives you the 0, and this term gives you 1, and so you have a pole of order 2. Okay, intuitively, that's not a bad way of thinking about what it is that's going on here. But yeah, so this thing has a pole of order 2, and z equals 0. What is then my residue? Well, by the theorem, my residue at z equals 0 of f, z is, since it's pole of order 2, this is going to just be the derivative of phi at 0. Okay. But then, what is the derivative of phi at 0? If this is phi of z, I can compute this derivative of this thing term by term here. Okay. And so phi prime of z at 0, this is minus 1 half, okay, plus 2 times 0 over 3 factorial, and every other term is going to have a 0 there. Okay, so I don't care about it, over this thing squared, right? 1 plus 0 over 2 factorial plus 0 squared over 3 factorial, and so on, all that squared. This is the quotient rule, right? Okay. But, of course, all those are 0, all these are 0, and so what am I left with? This is minus 1 half. And so the residue of this thing at 0 is minus 1 half. Okay. Okay. Now, this is not the only way that we could have found this residue. We could have actually found this residue by continuing on here and trying our best to deal directly with the Lorentz series for this thing, which is doable. Okay, through some algebraic trickery, we can definitely do this. Okay, by writing the Lorentz series, for instance, of 1 over e to the z minus 1, and then multiplying by 1 over z. Okay, that's another way of going about this. Okay, now we want to talk about zeros of analytic functions. So if your analytic function question is polynomial, right, then you're well acquainted with this. This is just a root of the polynomial. But we want to talk more generally about zeros of an analytic function. It's not necessarily a polynomial. And we want to see how those are related to poles. Okay, and so zeros of analytic functions and their relationship to poles. This is what we want to talk about. Okay, and so in order to discuss this, we have a definition. Our definition is 0 of order m. Okay. And our definition here is if f is analytic at a point z naught, then if f of z naught is equal to 0, and if there exists an m greater than 0, that's an integer, it's a positive integer here, okay, such that the mth derivative of f at z naught is not 0, but the m minus first, m minus second, every other mth order derivative that's less than, sorry, ith order derivative that's less than m, but the nth order derivative of f at z naught is equal to 0 for all n strictly less than m, then f is said to have a 0 of order m at z naught. Okay. Let's do a quick example of this. All right, so what about f of z, which is, let's say this is z squared plus 6z plus 9. Right? Okay, and let's look at this at, say z is equal to minus 3. Right? Okay. Then clearly f of z is, or sorry, f of minus 3, you can just check. So f of minus 3 is, this is going to be 9 plus 9 minus 18, right? And that's going to do it. Okay, so f of minus 3 is 0. Okay. And f prime of minus 3 is what? Well, f prime of z, let's just compute it real quick. F prime of z is 2z plus 6. So this is 2 times minus 3 plus 6. That's also 0. And what's f double prime of minus 3? Well, f double prime of z is equal to 2. Right? So this is just constant. This is equal to 2. That's not 0. So according to this definition, right, what is z equals minus 3 for this function? So then f, oh, that's not a good pin. So then f has a 0 of order 2, because the second derivative was the one that did it, that was non-zero here, and has a 0 of order 2 at z is equal to minus 3. Okay. All right. But you might have said, oh, well, intuitively, I actually completely understand what is happening here, because if I rewrite this, right, if I rewrite this, what is this? This is z plus 3 squared. So this is a polynomial, and thought of as a root, right? My old language for dealing with this is that this polynomial has the root z equals minus 3, and the multiplicity of that root is 2, right? We would call that a double root, right? And so this way that we went about doing this just gave us a nice way of characterizing what it meant to have a double root, right? A root of multiplicity 2 here for this polynomial. But note that this definition doesn't rely on f being a polynomial, right? Because if f is analytic at z naught, right, then these derivatives of any order that you like exist at z naught. And so if it has a 0, at z naught, then we can apply this. We can apply this definition to see what the order of that 0 is, for instance, right? So here, this is the key, right? This is the idea that we could do this for a function that is not just a polynomial. Okay, but there's a very nice fact here that even if our function is not really a polynomial, we have a characterization of 0 of order m at a point that is very similar to what happens, or what we know that happens in the case of polynomials. And so the following theorem gives us a nice characterization of zeros of order n. Okay. So what is this theorem? So let f be analytic at a point z naught. It has an order, or it has a 0 of order m at z naught if and only if there is a function g. There exists a function g which is analytic and non-zero at z naught, such that f of z is equal to z minus z naught to the m times g of z. Aha. Right? There we go. So what do you notice about this theorem? So I'm not going to prove this, but the proof's actually not, the proof's pretty straightforward. So this is in section 75 of the textbook. What is the idea here? This actually tells us, one, that our notion of 0 exactly matches up with our notion of multiplicity of a root of a polynomial if you're talking about zeros or roots of a polynomial. So if f is a polynomial, then this definition of 0 of order m is the same thing as a root of multiplicity m. Okay, so those two concepts match up exactly. 0 of order m is exactly the same as our concept of root of multiplicity m if f is a polynomial. So that's one nice thing you notice immediately. In that case, what is g, right? Well, g is the portion of the polynomial, right? So remember, you can fully factor these polynomials since they are complex, right? So if we're talking about a complex polynomial, those can be fully factored over the complex plane. And so this would be the portion of the polynomial that doesn't, that isn't 0. It's after you have you've pulled out every single copy of z minus z naught from this polynomial. So g of z is what's left. In that example we just did, where the only root of f was minus 3 and it had multiplicity 2, then g of z would be 1 in that case, right? Just the constant function 1. Okay, and so this fact also just gives us an extremely nice characterization of what it means for a function to have a 0 of order m, because a lot of times we're going to be dealing with a function, we know what the form the function has, and we can actually just see directly that it can be written in this form, and so we can actually identify the zeros in that way. Okay, all right, and so let's see some examples of how we can apply this to say to kind of list out the zeros of f. Okay, and so here's an example, again polynomial example. So let f of z be the cubic z cubed minus 8. Right. Well, I know that this thing has root z equals 2, for instance, and say that I've already, you know, divided out. By that, I've already factored out the z minus 2 copy. So this is z minus 2 times z squared plus 2z plus 4. Right. Okay. So this has a 0 of order m equals 1 at z naught is equal to 2, since I can write this as z minus 2 times g of z, where this g of z is analytic, right? So if this is my g of z, then g is analytic. It's actually entire, but g is analytic at 2. And also g of 2 is non-zero, right? So g of 2 is non-zero. It's actually 4 plus 4 plus 4, so it's 12. Okay. All right. The way that you would do this, of course, directly is you would just note, okay, f of 2 is 0. But what is f prime of 2? Well, it's 3z squared minus 8, right? Or sorry, it would be 3 z squared here. So this is, so note f of 2, of course, is 0, but f prime of 2 is 3 times 2 squared, so it's 12, which is non-zero. So this also tells you that this has 0 of order 1 at z naught is equal to 2. Okay. All right. Let's do another quick example. So what if f of z is z times e to the z minus 1? Okay. This has a 0 of order 2 at the point 0. Right? This has a 0 of order m is equal to 2 at z naught equals 0. Why? Well, I can find this just from the definition, right? So f of 0 is 0. Okay, what about f prime of 0? All right, well, f prime of z is, let's expand this. This would be, this is going to be z e to the z plus e to the z minus 1, right? So f prime of 0 is 0 plus 1 minus 1. So that's also 0. Okay. F double prime of z is, again, product rule gives you z e to the z plus e to the z plus e to the z here, so plus 2 e to the z. And so f double prime of 0 is 0 plus 2 e to the 0, so this is 2, which is not 0. Okay. So this has a 0 of order 2 at 0. Okay. So then what is, according to this theorem, so I did that by the definition, but according to this theorem, I should be able to write f as z minus z naught squared times g of z. So by the theorem, f of z should be equal to z minus 0 squared times g of z for some g of z analytic at 0 and g of 0 non-zero. And this is z squared times g of z. F is z e to the z minus 1. So what is the g of z in question? Right. So g of z is e to the z minus 1 over z. Okay. This has a removable singularity at z equals 0. Right. So, in fact, the g of z we take to make it analytic at 0. So this has removable singularity at z equals 0. If you don't believe me, just try to write out the Lorentz series here. You'll find that actually it's a Maclaurin series, right? So e to the z minus 1, you're subtracting off the constant term so that every single term has a z in it, so that when you divide through, you get what is left is a power series. It has no negative powers of z, and so this actually has a removable singularity, so all we have to do is define this in a way that it makes sense. And so we take g of z to be the piecewise defined function e to the z minus 1 over z if z is non-zero. And all we need it to be at 0 is 1. So 1 if z is equal to 0. This is the analytic function that's non-zero at 0 that works. Okay. All right. So there's a way to see how this works, even when you're dealing with something that's not a polynomial. Okay. Now the reason why zeros, this behaves a lot differently than talking about zeros for real valued functions. What's the reason for that? The reason why this behaves so nicely is because, well, for complex analysis, we have the fact that all of these things, right, that we're going to be dealing with they either have Taylor series or, at worst we're dealing with a Lorentz series thing. But specifically when they're a Taylor series, well, they're kind of like a polynomial, right? And if they're not, if they have a Lorentz series instead, well, again, still, they are kind of, sort of like a polynomial. Okay, and so the similarities, right, is a result of that formally, algebraically, these things are kind of like polynomials, right? Okay, so the next theorem. So the next theorem tells us that zeros of f are isolated in the similar way we talk about isolated poles or isolated singular points. These are isolated if f is not identically 0. Okay. So if f is not just the constant 0 function, these things are actually isolated. Okay, and so here's the theorem that says this. So given a function f and a point z0, suppose that firstly f is analytic at z0, and secondly that f of z0 is equal to 0, but f of z is not identically equal to 0 in any neighborhood of z0. Okay. Then f of z is non-zero throughout some deleted neighborhood. We'll make it epsilon here. It's the radius of z0. Okay, So then locally, some deleted neighborhood here, this thing is non-zero. Okay, the proof of this relies entirely on that previous theorem that says that if f has a 0 of order m at some z0, then that means that f has a very specific form. Okay. And then another related theorem tells you something about what happens when you have zeros that are not all isolated and what that means exactly for this f. Of course, you can, again, just looking at this, you can actually reinterpret this in terms of what I just said. Right, so the next theorem, okay, says the following: given f and z0, suppose the following. So suppose that f is analytic throughout some neighborhood n0 of z0. And secondly, suppose that f of z is equal to 0 at each z in some domain D or line segment L containing z0. Then f of z is identically 0 on the neighborhood n0. Okay. I.e. wherever it's analytic. Right. Okay. And so this is a counterpart to this theorem here that I've boxed. You box this in. That says that, well, if these things are not isolated, right, that is, if this thing is actually equal to 0 on, if this thing's analytic throughout a neighborhood and this thing is equal to 0 in some domain containing that point, so not necessarily that neighborhood, well, it turns out that actually it's equal to, it's actually identically equal to 0 on that entire neighborhood on which it's analytic. Okay. Now, the reason for stating these is to give you an idea of what it is that's going on here, and to kind of foreshadow the next fact, which is that zeros and poles are closely related to each other. Okay, in fact, it is going to be a major result for us that this is, we can say that zeros of order m cause poles of order m in a very specific way. Okay, so how does this work? It turns out that zeros of order m can cause poles of order m. How so? Well, let's suppose that, firstly, two functions p of z and q of z are analytic at z0. And secondly, suppose that p of z0 is non-zero and q has a 0 of order m at z0. Then the quotient f of z, which is p of z over q of z, has a pole of order m at z naught. Okay. So, it turns out that this is going to be kind of our main intuitive interpretation of kind of what to expect when you are dealing with a function that has a pole of order m at a point. The idea is that it looks something like this, right, in general. And so we'll have a specific statement that tells us, like, precisely what we mean by that. But here, going forward, this is what I'm saying, that if I have two analytic functions at z naught, and my numerator is not 0 there, then my denominator having a 0 of order m at that point means that the quotient has a pole of order m at that point. Okay. So, our favorite example we've referred to several times by now. If p of z is equal to 1 and q of z is equal to z times e to the z minus 1, right? So both of these, of course, are analytic. They're actually entire, so they're analytic everywhere. Okay. We also know that this has a 0 of order 2 at z naught equals 0. So this has 0 of order 2 at z naught is equal to 0. Thus, f of z, which is p of z over q of z, that is 1 over z times e to the z minus 1, has a pole of order m is equal to 2 at 0. But actually, we knew that. I mean, this is exactly what we found in the previous examples. Okay. That had a pole of order 2. Okay, at that point. Okay. All right. So, what about dealing with simple poles versus simple zeros, or zeros of order 1 here? Well, just like we had a theorem for computing residues quickly, in the case that we could write f in its nice form, right? Phi of z over z minus z naught to the m, right? We can apply similar thinking here for this idea to have a quick way of computing this residue, right? And so let two functions, so let p and q be analytic at z naught. Okay, if p of z naught is not equal to 0, q of z naught is equal to 0, and q prime of z naught is not equal to 0, then z naught is a simple 0, right? A 0 of order 1 for q, which means that the quotient has a simple pole, right? Then f of z, which is the quotient, has a simple pole at z naught, that is a pole of order 1, and the residue at z naught of p of z over q of z can be computed as p of z naught over q prime of z naught. So computing the residue of that quotient is easy in this case. Okay. So this is nice. Let's use this immediately, to compute residue at a point that we care about for cotangent of z. Right? What's cotangent of z? So cotangent of z is the quotient cosine z over sine z. Okay. Well, so this is a quotient of two entire functions, right? So p of z here is cosine z, that's entire. Right? Q of z is sine z, that's also entire. Where do I get singularities? Well, I get singularities at the zeros of sine z. So then I have singularities at z is equal to n pi, right, where n is an integer. Okay. But, of course, p of n pi is not a problem, right? This is minus 1 to the n, which is non-zero. And q of n pi is equal to 0 for any of these. But, of course, if I take q prime and evaluate it at n pi, well, this is also minus 1 to the n, which is non-zero. So these are all simple poles, right? Each singularity, so each c, which is n pi, is a simple pole of f. Okay, but the residue is actually easy to compute here. Okay, and what's the residue? So residue of at n pi of f of z. What is this? Well, this is, using our theorem, p of n pi over q prime of n pi, which is minus 1 to the n over minus 1 to the n, but that's 1. So the residue at any of those poles is actually 1. Okay. Let's do another quick example. So let's let f of z be equal to hyperbolic tangent at z over z squared. Or another way of writing this is sinh z over z squared cosh z. Okay. All right. Well, and let's compute, I want to compute the residue at the point pi I over 2 of f of z. Well, first of all, is this a singularity? Yeah, it's a 0 of the hyperbolic cosine. Okay. And so, in order to compute this, right, this is what I want to compute, I write p of z is hyperbolic sine. I write q of z to be this denominator z squared cosh z, right? So then p of pi I over 2 is sinh of pi I over 2. What's sinh of pi I over 2? This is actually I times sine of pi over 2. So this is just I, which is not 0. Okay. Of course, q of pi I over 2 is equal to 0. But what about q prime? Q prime of pi I over 2 is, if I'm taking the derivative of q here, so this would be using product rule, if you like here, this would be this would be 2z cosh z plus z squared sinh z so this would be plugging in at pi over 2, since that's a 0 of Cauchy, that term cancels. And so we're only left with the single term in the derivative, which is pi I over 2 squared sinh of pi I over 2, which is minus pi squared over 4 times I, which is again non-zero. Okay. So this is a simple pole, and to compute this residue, all I have to do is compute p of pi I over 2 and divide by q prime of pi I over 2. And so what I get is that this residue, here, maybe I'll write it here so I have more room. This is minus 4 over pi squared. Okay. All right. Now, you might say that, for going in the other direction, when we had this theorem that allowed us to write, if we knew that a function had a pole of order m at a point, it allowed us to actually write it in a special form and then use that theorem to compute the residue there, depending on the order, not just if it was a simple pole, right? Not just for order 1, but also for higher orders. So I'm looking through for my theorem here. So here, this thing, right? So this allowed me to compute the residue even if my pole had higher orders here. So is there a theorem, right, that allows us to do this for the zeros of higher order here, right? Because this theorem, going back here, this theorem we're only applying at simple, or at zeros of order 1, which turns into simple poles here. Could we do this for zeros of higher order so that this thing doesn't have a simple pole, it has a pole of some order m? The answer is yes, but those formulas are nastier and they're not really practical to use like that. Typically, it's easier to do something else. And so that's the deal. Okay. So now we want to talk about behavior near singular points. And this will kind of nail down the last remaining intuition about what happens here. And then finally, we can move on to some more applications of the residue theorem here. So, so behavior of functions near singular points. Okay. And of course, we're interested here in isolated singular points. Behaviors to extreme otherwise. So these are by far the most important category of these things that we're interested in. Okay. And so some simple facts here. So theorem, if z0 is a pole of a function f, then obvious fact, the limit as z approaches z0 of f of z is infinity. So poles are exactly what you think they are. Okay, so this is just a quick fact here. I'm not going to prove any of these facts because actually we don't apply these anywhere. This is just kind of a nice list of intuitive properties that you can expect these things to have. So what's another fact here? If z0 is a removable singularity of f, then f is analytic and bounded in some deleted neighborhood of that singularity. So then f is analytic and bounded some deleted neighborhood of Z naught. Okay. Okay. And lastly, we have a theorem that is related to, well, it concerns the behavior at an essential singularity. Now, we've already talked about Picard's theorem. So Picard's theorem gave us, that was last lecture. So Picard's theorem told us something about behavior of f near an essential singularity. And it's actually a stronger result than what I'm about to state. But here is another result that is slightly weaker than Picard's theorem. But it also tells us what's going on here. Okay. And this is known as Casarati-Weierstrass. So here's a theorem. This is usually called Casarati-Weierstrass. So what does this say? This says that in each deleted neighborhood of an essential singular point, a function assumes values arbitrarily close to any given number. So actually, we know by Picard's theorem that it has to assume the value of every single number minus one possible exception, right? So suppose f has an essential singularity at Z naught. Okay, let W naught be any complex number. Then for any epsilon that's positive, this inequality, that is value function of f at z, and W are, and W naught are epsilon close, this is satisfied at some point z in each deleted neighborhood of Z naught. Okay. All right, so this is a weaker form of Picard's theorem. Picard's theorem actually says you attain those values minus one possible exception, right? And not only that, but you attain those values infinitely many times, right? So Picard's theorem not only says that that you actually attain those values except for the exceptional point, you attain them infinitely many times, right, in any neighborhood of an essential singularity. Okay, so both of these, both Casarati-Weierstrass and Picard's theorem, tell you that near an essential singularity, this function is going absolutely nuts, right? And so this just gives you a nice splitting of the behavior of these functions in a way that, by now you understand, okay, well, so the removable singularity is nice because actually there's not really even a singularity there. We can be smarter in how we define the function, and we can remove it, right? That's what is said by this second theorem that I boxed. The first theorem that I boxed tells me that poles behave in exactly the way that I'm used to from like Calc 1, my early days of sketching, say, the graphs of rational functions, right? Poles are behaving in exactly this way that I expect, right? Maybe like this is behaving like in this way that for real valued functions like asymptotes, right, did, where you had an asymptote where, say, on both sides of it, the function approached infinity or minus infinity or something. Okay, so here, this is an easy, this is an easy description here of a pole. And then for an essential singularity, what's going on is kind of a nastier, less regular thing. So an essential singularity is, in some sense, less controllable. Okay. And so now, finally, we can apply the residue theorem. All of the stuff we've been doing since the residue theorem has been computing residues, right? We actually, in most of those examples that we did, we weren't too terribly concerned with computing integrals. The reason for that is the residue theorem says that computing integrals is really easy if you know the residues, right? So like if you can compute the residues, you can compute the integrals. So the residue theorem just says it reduces the problem of computing these contour integrals to computing residues, right, at singular points. And so ultimately that's the deal. In all of these examples where I went through and computed residues, now you can think of it as kind of like you have a catalog where if I go through and ask you to compute, if I ask you to compute a contour integral involving a contour that goes around those singularities in questions where you computed those residues, well, you can do that using the residue theorem really easily. Okay, and so that's the idea. So very much so when you're practicing these things on your own, being able to compute residues quickly is kind of more important, since if you can compute the residues, then you can just write out what the contour integral is using the residue theorem. Okay, so we can apply the residue theorem in many ways. One way is to the computation of improper integrals of real valued functions. So when I sat down to plan what it is that we would be covering this semester, this was the ultimate application that I wanted to cover, because this is kind of like the ultimate justification for complex analysis being a very cool thing to study, because imagine for a second you didn't know anything about complex, and you were just interested in computing some improper integrals of real valued functions. Okay, so you come across an improper integral, you have no idea how to compute this, if you can even compute it directly, and then someone comes to you and computes it, right, writes out the answer. You actually check, maybe numerically, and say, yeah, this is actually the answer. Like, how did you find this? And they say, well, I did it, using complex valued functions, right? This is kind of like the ultimate justification for complex valued or complex analysis and the study of complex valued functions, being nice and important in that even if you originally viewed this as just some kind of thing that maybe you found it independently interesting, you weren't that worried about its applications, now all of a sudden you have, oh wait, like, knowing something about complex valued functions and their behavior tells me how to compute integrals involving real valued functions that don't reference complex numbers in any way. Right, so this is the idea, and this is the thing that's so nice, right? Okay, and so just a quick reminder for improper integrals, right? So say that we want to compute an improper integral of a function that is real valued, right? And we'll say that all we need is f to be continuous over the half open interval from 0 to infinity. Right. Well, in that case, how did we define this, right? Going back to Calc 1 or Calc 2, whenever was the first time you saw this? Well, you define this as a limit. So you say the limit is r goes to infinity of the integral from 0 to r. And the reason you had to do this, of course, was because this integral was something you could compute, because this is an integral over a finite interval, right? Whereas this, what is this, right? How do you deal with that? Well, the way you deal with that is you can compute these integrals, and then you can take a limit, right? These are going to depend on r in some way typically. Then you take limit, and that tells you exactly how this works. If this limit exists, we say that that integral converges, and it converges to that value, right? If it doesn't exist, this limit doesn't exist, we say that this diverges, right? So if this exists, we say this integral converges to that limit. Okay. All right. What about an improper integral that is of this form? What does this mean? Right. Well, you had to choose some splitting point, right? To make our life easy, we can split at 0. But of course, there are instances where you'd want to split somewhere else. This depends on, the integrand itself may have points at which it's not defined, in which case that is also considered an improper integral. Right, so there were two types of improper integrals. There were ones that had, they were improper because of a limit of integration, was infinity or minus infinity. And there's improper integrals that were improper because you're integrating over an interval on which the integrand was maybe not defined at one or more points, right? And so, in either case, these involve limits. So in this case, the way that we'd write this is you would take the limit as, say, r sub 1 goes to minus infinity of the integral from r sub 1 to 0 f of x dx. And this would be added to the limit as r sub 2 goes to positive infinity of the integral from 0 to r sub 2 of f of x dx. All right, so here's how this would work if you're dealing with a function f that's continuous on all the reals, right? Okay. And so this thing converges if both of these limits exist, and we say it converges to their sum. Okay. And so there's another way of writing this sometimes more conveniently. So, and we do this using something called the Cauchy principal value. So another way of writing this improper integral okay, we write PV here of this thing. And we say that this is equal to the limit as r goes to infinity of the integral from minus r to r of f of x dx, provided this single limit exists. This is known as the Cauchy principal value. And that's the reason for this PV here. Okay. Okay. So it turns out that if this integral that I just took away, so if this thing converges, okay, then this Cauchy principal value exists, and this value is exactly the number to which that integral converges. Okay. But the converse is not true. So, in fact, if what's the nicest way to put this? Let's write this as star. All right. So if this thing converges, so that improper integral. So if star converges, then its Cauchy principal value exists, and it is the same. So then it's Cauchy PV exists and is equal to this value to which star converges. The converse is not true, though, okay? But it is not true, okay, that if the Cauchy principal value exists, then star converges. Okay. Here's an example that illustrates this fact. Okay. So what is the Cauchy principal value of the improper integral minus infinity to infinity of x dx? All right, so this is the limit as r goes to infinity of the integral from minus r to r of x dx, okay, which is the limit as r goes to infinity of x squared over 2 evaluated from minus r to r, but that's 0. So that exists easily. Okay, but if I actually compute this in the long brute force way from Calc 2, by splitting this as the limit as r sub 1 goes to minus infinity of the integral from, r sub 1 to 0 of x dx plus the limit as r sub 2 goes to positive infinity of the integral from 0 to r sub 2 x dx. Okay. Then what I end up with is the limit as r sub 1 approaches minus infinity of x squared. So this is x squared over 2 evaluated from r sub 1 to 0. Okay. All right. And this is plus the limit as r sub 2 approaches infinity of of x squared over 2 evaluated from 0 to r sub 2. Okay. But these limits don't exist, right? So this is minus the limit as r sub 1 approaches infinity of r sub 1 squared over 2 plus this limit as r sub 2 approaches infinity of r sub 2 squared over 2. Okay. These last two limits don't exist, right? They're infinite, and so this fails to exist. So D and E. Okay, so this doesn't work out this way. Okay. All right. But there are certain conditions we can impose on this thing that guarantees that Cauchy principal value existing gives us what we want. Okay. All right. So, but if f of x is even, remember what that means. So if f of x is even, i.e. that means that f of minus x is equal to f of x for all x. So it's symmetric with respect to the y-axis. Okay, and if its Cauchy principal value exists, okay, then its improper integral, which is the integral from, say, minus infinity to infinity of f of x dx, is actually equal to its Cauchy principal value. And so we can compute this directly from it. Why? Use symmetry, right? Use symmetry of f about y-axis. Okay. If I use this symmetry, then if I compute the integral, say from minus r sub 1 to 0 of f of x dx, this is the same thing as half of the integral from minus r sub 1 to r sub 1 f of x dx, right? Okay. Similarly, the integral from 0 to r sub 2 of f of x dx is equal to 1/2 of this thing, right? So it's equal to 1/2 of, say, minus r sub 2 to r sub 2 f of x dx. Okay. And so, what I can do is I can say, if I take the integral from minus r sub 1 to 0 f of x dx plus the integral from 0 to r sub 2 of f of x dx, then this is 1/2 times the integral from minus r sub 1 to r sub 1 f of x dx plus 1/2 times the integral from minus r sub 2 to r sub 2 f of x dx. So I can take the limit here as r sub 1 and r sub 2 go to infinity. All right, so let r sub 1 go to infinity, let r sub 2 go to infinity. What do I get? Here, on the left-hand side, right, I get the left-hand side here, this thing I've boxed. And here on the right-hand side, I get the Cauchy principal value. Okay. So also, directly from this, under the same assumption, so f is even, and its Cauchy principal value exists, the integral from 0 to infinity of f of x dx can be computed as 1/2 Cauchy principal value. Again, just directly from that fact. Okay. All right. So, next, we finally show a way of computing these improper integrals using residues. But I'll do that starting tomorrow. Okay. All right. So that's that. Like I said, we got one more thing to do here, and we are done with the course. Okay, so I will see you all tomorrow.